The evaluation of alternatives using the annual worth or AW method is usually easier to apply than the present worth method for several reasons summarized in this presentation. An AW value is easy to understand by virtually any individual, since it is an expression in local monetary units per year, such as dollars per year, euros per year, pesos per year. The term AW is known by other titles. Some are equivalent annual worth, annual equivalent, the equivalent uniform annual cost, EUAC, and others. All of these result in the same numerical value and the same economic decision. The primary advantage of AW over present worth and other methods stems from the equal service requirement. The AW method for mutually exclusive alternatives requires that the AW value be determined over only one life cycle. The respective lives of each alternative are used in this determination. The resulting value is the AW for all future life cycles. Thus, the equal service requirement is satisfied. In all cases, AW, PW, and future worth, or FW, can be determined from each other using this relation. The value of N in the relation is the LCM of lives, or the specific study period that has been used for the analysis. Finally, let's consider the question of assumptions. They are exactly the same for both PW and AW evaluation. That is, the services needed for the LCM or study period, there is repeatability of the life cycles, and the cash flows are stable, or they move in direct accord with the inflation rate. With these facts, we are ready to proceed with the details of the AW method. They are quite simple. All AW values have two distinct components: a capital recovery, or CR component, and an annual cost, or operation of the alternative component. If revenues are estimated, they are included in this equivalent annual amount A. What does capital recovery actually mean? It is the new equivalent amount of money that the alternative must generate each year to get back exactly the initial investment plus whatever the stated return is. Capital recovery, therefore, is, in engineering economy terms, an A value. Suppose you get a laptop computer and use it to develop graphics for video game clients. If you want to recover your cost of the laptop plus, say, 8% per year, then the capital recovery is the total amount that you must earn each year over your estimated useful life of the laptop. Say that's 3 years. The relation to calculate capital recovery is shown here. The first cost P is spread out over the expected life at I%, and any salvage value S is removed because this S is an anticipated quote-unquote revenue each year once the AF factor is applied to it. It's time for an example of capital recovery. Here's the problem. A $200,000 asset is purchased. It has a life of 10 years and no salvage is expected. How much equivalent new revenue must be realized each year to recover the cost and the return of 15% a year? Here's the answer. With a P of minus $200,000 and an N of 10 and a salvage value of 0, the equivalent A, or the capital recovery value, is an amount of $39,850 per year. To ensure the 15%, this should be an annual amount realized, which totals to $398,500 over the 10-year life. In other words, the output of the purchased asset must produce enough revenue each year so that this equivalent of $39,850 is, quote, in the bank. If a spreadsheet function is used to determine capital recovery, the PMT function displays the capital recovery amount using this format. Note that the sign on the first cost P is plus and on the salvage value S is minus. This ensures that the PMT function returns the correct sign of the input variables. Now that we understand and can calculate capital recovery, let's add the annual cost, which is the AOC, or the maintenance and operation, that is M&O cost. The result is AW is equal to capital recovery plus this A amount, determined over one life cycle at the MARR. For the economic decision, use the guidelines shown here. For one project, when the AW is greater than or equal to 0, the project is justified. If there are two or more mutually exclusive alternatives, the alternative with the numerically largest AW value is the one selected. If the analysis is performed over a study period rather than the LCM, then the AW is determined over exactly this period of time, and the selection criteria is the same as shown above. Finally, let's consider independent projects. They are always exempt from the equal service requirement since they do not compete with each other, only with the do-nothing option. Determine the annual worth over the respective lives of each project and select all of those projects that have an annual worth greater than or equal to 0, provided there is no budget restriction. Here is a complete annual worth evaluation of two different life systems. The P, AOC, S, and N estimates for the two systems are made. We want to calculate the annual worth at 12% per year. For System Q, which is a 4-year life X-ray system, the first two elements of this annual worth relation determine the capital recovery amount, while the last amount of the minus $15,000 is the AOC. The total annual worth for Q is minus $23,412. This is the CR and the A amount added together. Similarly, the total annual worth for System Y is calculated, and its value is minus $27,052. As you can see, the AW value for Q is numerically larger. That is, the equivalent annual cost is lower. Therefore, choose System Q. This is a screenshot of an Excel solution for the same analysis. To find the AW values in one function, embed an NPV function within the PMT function as shown here. This function is for System Q. Here we have a 4-year life that is used for N. As can be predicted, the AW values are the same as with the manual solution. Once again, System Q is the winner. Well, that's it for the AW method. It is much easier to apply than the PW method, especially when different lives cause the LCM value to make the analysis rather messy from an arithmetic perspective. As always, thanks for your attention and interest.